Hello, everyone. Happy Friday. Sorry for my untimely quick exit on Wednesday, but the power went out here. So I will aim to pick up exactly where I left off with maybe a little bit more context because we kind of left off at at an unplanned point. Announcements before that happens. Let's see. Oh, homework. Your homework from the OFDM module is due today. An extension has been granted for one student, so I decided to extend it to all students to 5 p.m. So you have until 5 p.m. today to submit. Also, I'll repeat the announcement about 526 is if you're an undergrad and you want to take 526, send me an email and that'll kickstart the registration process. Okay, any questions from you all before we get back into the land of ham? All right. So let's just take a moment and re-familiarize ourselves with what's going on. We've now decided to look at sequences of bits as vectors in vector spaces. We had to modify our notion of what addition of vectors meant, and all of our vectors can only have coefficients of ones and zeros. But if you do that, then it's completely legit to think about sequences of length k as being vectors in a vector space. Then sequences of length n would be vectors in a different vector space, but a vector space nonetheless. This is akin to R2 and R3 both being vector spaces, but you wouldn't ever talk about an R2 vector in an R3 space. Or if you did, you'd talk about projection and all that stuff. But okay, so that's the introduction that way. And then we were talking about once you have a fixed k, so a length of your data word, that defines that there are 2 to the k possible data words. And so then your space of data words has 2 to the k elements in it. Your code words will have to be longer than your data words, or else you're not doing error correction, you're doing compression. So n will have to be strictly larger than k, which means that there are more vectors in the code word space than in the data word space. And so the game we now have to play is, how do we map data words to code words? Because there are going to be more vectors in the code word space than we need, because we only need 2 to the k of them. So the real game in the sport of error correction coding is, can you identify a function or a mapping to take data words to code words? And depending on that choice, how good is your performance? How many errors can you reject? How many errors can you detect? That kind of deal. So to help us on that path, we are going to be exploring what's called the Hamming bound. And the avenue to get there is to just explore how many, in a sphere of radius t, a Hamming sphere of radius t, how many code word vectors in the code word space are there? And so that's actually what we have here. So this, if you do sorry, I left the parentheses there. This is the number of code word vectors, so vectors in the code word space, in each sphere of radius little t. Right? You make t smaller, then you'll have fewer vectors. If you make t bigger, you'll have more vectors. And remember, we like to have large Hamming spheres. We like to have large non-overlapping Hamming spheres, because remember, in this picture, the bigger your Hamming sphere is that doesn't overlap with any other Hamming sphere, the more errors you can automatically detect and correct. All right, so here we had a sphere of radius 1 around each code word, and that means we can automatically correct any 1-bit error. If we pick a bigger code word space, we might be able to draw Hamming spheres of radius 2 that don't overlap, in which case we could correct 2-bit errors. Okay, so that's where we're going. but for now, let's pick up where we left off. So this has to be less than or equal to 2 to the n, because there are only 2 to the n vectors in the code word space. And so this means if we divide both sides by 2 to the k, then we get the sum j runs from 0 to little t of n choose j. And I didn't point this out here, but I think we've defined somewhere in a math textbook that n choose 0 is defined as 1 for at least for n bigger than or equal to 1. It's probably also true for n equals 0, but that's not going to be relevant for us. But if you're looking through your notes later and you say, how do you do n choose 0? It's just defined to be 1. Right? I mean, kind of. How many ways are there to pick 0 things out of n things? Only one way? I don't know. It's fine. It has the same thing to do with like what is 0 factorial. We call that 1. Okay, so right, divide both sides of this inequality by 2 to the k, and we get the following inequality. This sum of possible choices has to be less than or equal to 2 to the n minus k. And this quantity n minus k is important enough that it gets its own variable name sometimes. This is sometimes called little m, and this is the frame check sequence length. Right? It's the number of bits that you're going to append to every k length data word to make it into an n length code word. Okay. So this actually right here, this entire inequality, is called the Hamming bound. Oh gosh. And it's a function of 3 variables, right? It's a function of k, n, and t. And this Hamming bound is, it's called a necessary but not sufficient condition. Necessary but not sufficient for t error correction. That is, if you want to be able to correct 5-bit errors, then your choice of n and k must satisfy this for that given t equals 5. Okay. You can't choose an n and k smaller than whatever this bound dictates, or else you physically won't be able to pack Hamming spheres of radius 5 into that space. Okay. So I guess we can try a quick example of this. Let's say, and I mean you can fix any 2 and solve for the third. That's one way to work this. Let's say we want to be able to correct for 1-bit error, so I set t equal to 1, and then I need to solve for 2 to the n minus k. What are the n's and k's that make this true? Greater than or equal to sum from 0 to 1 of n choose j, and that is 1 plus n. And so what does that mean? We can solve this, and it says that n has got to be 2 to the m minus 1. This is a sum on j. Okay, so for example, if I let m be, well, 3, so if m equals 3, that tells me that n has got to be 7, and that tells me that k has got to be 4. Okay. So what does this say? This says if you have data words of length 4 bits and you have code words of length 7 bits, then there is a potential to pick a mapping that corrects for 1-bit errors. It doesn't tell you what that mapping is. It just says that you meet the necessary conditions for an error-free code. Okay, so that's I feel like that is the crucial observation from this part of the lecture, is that this is well, so first off, it's a necessary condition, not a sufficient condition. But worse than that, in some sense, it doesn't give you a way to pick the mapping. It just gives you a way to test, is the n and k that you want even remotely feasible? Okay. So for example, if I wanted to send 4-bit data words as 5-bit code words, this would tell me that I cannot meet the Hamming bound for any t bigger than 0. So that means that is impossible to pick a code that takes 4-bit data words, maps them to 5-bit code words, and guarantees any kind of error correction. In fact, it says that for k equals 4, n equals 7 is the smallest n for which we can ever expect to get an error-free code, or for a 1-bit correcting code. I think if you do this, you would also work out that you can't get a 2-bit correcting code mapping from K4 to N7. Questions on this? Well, the reason I picked 4 and 7 is because this is the ideal segue into your very first error correction, practical error correction code, and that is Hamming 7.4. So a bit on notation here. When you see error correction codes listed like this, they will often be a name followed by a sequence of numbers. That sequence is usually n is the first thing, k is the second thing. Okay, so this is how I would say the Hamming code that maps data words of length 4 to code words of length 7. There are also Hamming 12.8. So these numbers increase larger and larger. And one thing to keep in mind when we go through all these is something called the code rate. And it's very simple. It is the ratio of k over n. Now this represents an efficiency measure, or its reciprocal represents a bloat measure. Right? So the smaller your rate, the less data you're getting per bit sent. Okay. So for example, like the silliest error correction code is for every bit I want to send, I'm going to send 10 bits that are all just replications of that bit. That would be a rate 1/10 code. And it would work. It would be very inefficient, but it would be a way for you to be able to correct for very, very noisy channels. Okay, so let's talk about the specific structure of Hamming 7.4. So what we're going to do is data words are length 4, so our data word can be represented by 4 bits, and I'm going to write them right to left here. And we know that they're going to map to a code word of length 7. So let's give ourselves 7 boxes here. 1, 2, 3, 4, 5, 6 lines makes 7 boxes. And so the rule for Hamming codes is the check bits. Right? Remember, FCS is frame check sequence. It's the number, it's the bits that you're adding on to do your checking. The check bits in a Hamming code are always placed at positions within the code word that are multiples of 2. So, for example, this is an n equals 7 code word, and that means we're going to put a check bit, a check bit, a data bit, a check bit, and then a bunch of data bits. Okay, so let's talk about positions here. This is position 1, 2, 3, 4, 5, 6, 7, right? Hamming 7, 4. And again, you don't have to do this right to left. You could do it left to right. But I guess for whatever reason, I've got mine right to left. And what's also going to be nice is if we can write these as binary numbers. So the positions themselves, it's nice to have them in binary form. So the positions in base 2 are, well, 0, 0, 1, 0, 1, 0, 0, 1, 1, and roll it over. Okay. So I've numbered the positions 1 to 7, and I'm sorry if you're a CPU whiz and your mapping to binary is automatic, but mine is not, so it helps me to write all this out. And I've written those base 10 numbers, those base 10 positions, position in base 10, as also positions in base 2. Okay, so to build the check sequence, so the frame check sequence for a Hamming code, you follow the following rule. You are going to XOR the positions in base 2 where the data is high, is 1. So XOR all of the base 2 positions in the code word where the data is 1. So let's pre-populate this. So the data is going to be D4, D3, D2, and D1. And so depending on which of these Ds are 1s and which of them are 0s, I'm going to have a variable length XOR. So I think it makes sense to start to work through an example. So let's parallel this with an example. So the data word I'd like to transmit is 0100. Okay, so now let's build the code word. 2, 3, 4, 5, 6. And let's place the data bits inside. So 0, 1, 0. And then this is the last data bit. Okay, so to build the frame check sequence, we take the XOR of all the positions where the data is high. So the frame check sequence is the XOR. Well, it's just one thing, so it's going to be kind of trivial in this case. The position is 1, 1, 0. And XOR with nothing. Okay. So it's the trivial XOR. Okay, so then we take these check bits and we place them into the code word at the power of 2 positions. Okay, so and then it's ready for transmission. We have built the code word, and I have actually given you a way to construct the mapping. Any length 4 data word now can be turned into a length 7 code word using this format by telling you where to put the data bits, how to get the check bits, and where to put them. Okay. And then note that because my positions are going to be length 3, the XOR of these 3 length sequences are going to also be length 3. So my frame check sequence will always be length 3. So I only have 3 slots, so I only get 3 check bits. Okay, so now we're ready to talk about what does the receiver do? And if you think back to this picture, the idea is that the receiver runs the same procedure on the data bits that it receives. And so let's implement that. So at receiver, it's going to extract the data bits from the places that it should have data bits, and it's going to do the same XOR procedure on those. So build XOR prime. Build FCS prime.
But I'm a little confused. I understand where the 110 came from. That came from position D, position 6, where
Yeah,
that's a 1. But what are we XORing it with?
with nothing, and so that's why it's just not the best example in the world. So here, I'll start a second example, and I'll truncate this a little early. So if our data was 0, 1, 0, 1, then our frame check sequence would be the XOR of position 6 with position 1, 2, 3.
Oh, okay. I got you. And then if
Yeah,
you had 3 ones, then you would have an XOR of 3 things.
exactly. And then the other notable point is that the XOR of 3 strings, XOR is associative. So I do XOR of the first 2, and then XOR of the result of that with the last.
Yeah,
It
got you.
works just like addition. Okay, so just to finish this thought, this would be 1 XOR 0 would be 1, 1 XOR 1 would be 0, 0 XOR 1 would be 1, and so now this would be the frame check sequence for this data word. Cool. I'm sure other people had that question, Ricardo. Okay, so let's, if you don't mind, let's run 2 received options here. So I guess I'll leave that up for now. So let's do scenario 1. And that is no errors. That means that our received code word, our received sequence is 0, 1, 0, 1, 0, 1, 0. Exactly what we sent. Okay, so then the receiver says, I know the scheme, so I'm going to pick out, these are my data bits. So data prime is going to be 0, 1, 0, 0. But we don't know if this is error full or error free at this point. And so the receiver then says, okay, the positions where the data is high is, in this case, just position 6. So the receiver does the same procedure and does the XOR of 110 with nothing and gets 110. And then it matches. It looks. Does that match with that? Does that match with that? Does that match with that? And if the answer is yes, then the conclusion is no error. We can pass this on with some confidence. Okay. So, I mean, you would hope with any of this is that when no error occurs, no error is detected. Like that is the base requirement for a reasonable error correction code. But
So is D prime the same as D, or is this another signal? Where did we get D prime from?
At the receiver looks at the data slots, and the data slots are here, 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 and here. And so the receiver knows which slots are data slots, and so is able to pick those bits out.
Okay.
So let's work through scenario number 2. Okay, so in scenario 2, I'm actually not going to tell you what happens. I'm just going to tell you what the received bits are. And we'll together, we'll work out what happened. So the received string is 1, 2, 3, 4, 5, 6. And let's see, we receive a 0, 1, 1, 1, 0, 1, 0. Now, I know that you all can just look at the top of the board and pick out which bits were flipped. But let's pretend that we're the receiver and we don't actually know what bits were sent. The only thing we know is what's in front of us. I'm looking at 0, 1, 1, 1, 0, 1, 0. Okay, so at the receiver, my D prime is 0, 1, 1, 0. Okay, so I see data bits here, 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 and here. And that means that these are the positions. So FCS prime is going to be the XOR of all the positions of all the high data bits. So this is going to be the XOR of 6 with 5. So let me see if I can. So this was position 6. This was position 5. And if there were more 1 data bits, we would have more XORs to do. Okay, so let's do this XOR. This is going to be false, and then true, and then true. And so then we say, well, wait a minute. What is the true FCS? So FCS is, well, we pick them out of the check bits. It's 1, 1, 0. And those came from the check bit, the check bit, and the check bit. Okay, so at this point, at the receiver can conclude at least one error occurred, right? Because the frame check that it should have got is not the frame check that it computed. Therefore, there was at least one error. What follows is, if there was exactly one error, let's try and see if we can correct for it. So the way to do that, and this is actually the brilliance of the Hamming code, is because if we were to do an XOR between FCS prime and FCS, what do we get? We get true, false, false.
Which is true, false, true.
Okay. Yes, you are correct. Good, because I was about to say this is the position in base 2 of the error. Okay, so that's position 5, which means we found an error there, which means this should have been a 0, which means the data is actually accurately represented, because now our data matches with our data.
Okay. Well, actually, I get most. I was wondering why the FCS. Is this just an example that you picked that FCS is 6 and 5 at each bit, or would it go through each each section, like it would go through like 7.6, 6.5, and
So so for this, the frame check sequence is only built out of places where the data bit is 1.
okay.
So where the data bit is 1, that's how we built the original FCS, and that's how we build the FCS prime. Is we look at all the slots for data bits, and those slots that are high, take those positions and then XOR them.
Okay. So if you had, so if you had more than, let's say if it was just 1111 for your data, would you do it multiple times FCS?
Mm-hmm.
Okay.
Well, you would do multiple XORs. So
Yeah.
I guess we should talk about that. What happens when I want to XOR multiple things? So let's try, if all the data was 1, that would be 111 for position 7, 110 for position 6, 101 for position 5, and then 011 for position 4. So how do you do an XOR of more than 2 things? Well, like I was saying, you can do it pairwise. So these two give you false, false, true. These two give you true, true, false, and then you can like XOR in this way is what they call associative. So I could do these two, and I could do the result of that one, and I could do the result of that without that one, or I can do them pairwise. So let's just finish this. This would be true, true, true. Okay, so a data of all ones actually leads to a code word of all ones, coincidentally.
Okay. Is that why? Oh, is that why? If that's why you only could do one, because is that because I'm still confused. If you have, if you get the right FCS value that you want compared to your if you get a different one, then it's between now. I don't know how to explain this. I guess it's between. So looking at like the XORs and XORs, and so we're comparing 111 to 110 that we've used for for our check bits. And then
okay, so hold on. Let me see if I can keep up with what your scenario is. So you're saying this is scenario 3, in which 1, 2, 3, 4, 5, 6. Now we're receiving data here, but we have the same FCS as before?
Yes, I guess. And I was just wondering, like, so that's it's different that way, and then if you XOR it, you can find. But does that only find the position? Oh, I guess it would find the position. Okay, I see. It does still find.
Okay, so yeah, in scenario 3, this is FCS prime, right? Because this is all of the data bits in the received vector are 1, so I have to do a 4-way XOR. Once I do that, I get all 1s, but FCS that we received is 110. And so what the recipe calls for that I just told you is to XOR these, and that should give you the position of the error, and that results in false, false, true. So it says that position 1 was the error.
Okay.
Now this is a problem.
Yeah, that was my question, I guess, in that sense, yeah.
So, okay. This is a problem because Hamming tells us that position 1 should have been a 1. And this gets at that this is a, well, I don't know. Can I throw this out to the class? Why? My claim is this is working as intended, but it's not good. Can anyone articulate why or what's going on or anything? Is anyone with me?
Well, I mean, your code word is basically your indicator of how the system is working, and right now your indicator is just wrong. So you basically get false information.
But I think that the scenario is the same transmitted code word. So this is being transmitted. This is being received. And so actually my point is the transmitted FCS is coming through loud and clear. It's coming through correctly. But how many other bit errors were there? Or how many total bit errors were there?
There were 3.
There were 3 errors. 3 errors. They happened to all be data bit errors, but 3 bits in 7 got flipped.
Is that why you say, I guess, why you only can do look for a position, you only can find 1 error?
Because Hamming 7.4 is a 1 error correcting code. It can only handle 1-bit errors correctly. If you hand it something with 3-bit errors, it will execute. It won't fail. It won't complain, but it will give you the wrong answer.
Can it do single bit errors in the check bits?
Yeah, let's try that. Let's try scenario number 4. It would be really it would be really unfortunate if you needed your errors to be in specific places, because that's unreasonable even by my standards. So let's try scenario 4. And at the receiver, we'll go 1, 2, 3, 4, 5, 6. And we'll say that the data bits come in loud and clear. And let's say that the last bit gets flipped. So check bit number 1. Okay, so FCS prime is going to be same as it was before. It's XOR of 110 with that's it. And then the thing that we're comparing it to, which I'm going to call FCS, but that's a lie because it's only the received FCS, and it's going to be 111. So these don't match, which means we suspect an error occurred. So let's XOR that, and we get false, false, true, meaning this bit was an error, meaning the data bit's fine. Go ahead and pass that on to the application that wants it.
Oh, so was scenario 3 a false negative in some sense?
No, well,
because
we saw that we claimed that an error occurred, but we didn't correct it correctly.
Okay.
And it's very insidious, right? This means that you can't trust your error correction code for more than it was designed for. That if you're in a channel in which more than T bits are likely to get flipped in every frame, you need a different error correction code. Which means you're going to have to pay for that with a lower code rate because of the Hamming bound relationship. That if I want fatter spheres, I need a bigger N and a fixed K. That means my code rate diminishes, which means I'm sending more bloat for every data bit. But if your channel's flipping bits left and right, I mean, you got to do what you got to do.
So would we say like if scenario 3 is just wrong, I guess, in every way, then scenario 4 is like a false positive in some sense? Or is the system would say that, oh, if it's checked, if that's error, then okay.
Yeah, okay. Yeah, this is what I was calling a false positive on Wednesday's lecture. Yeah.
Okay.
But we're able to correct for it. So I don't know if it belongs in the column of true false positives.
Yeah.
Oh my God. Could I have picked a worse phrase? A true false positive?
You defined a false positive.
But you're able to correct for it. So okay. I don't know if it really should count against us.
Okay.
Okay. I think in a normal class, this is when I would actually give you a challenge. Would you like a challenge? I got one head.
I love challenges.
And okay, all right, Sandra, you have been outvoted. Okay, so I will put it in the center here, and I'll put it in a different color. If we receive the following, 0, 0, 0, 0, so 5 zeros and 2 ones. The question to you is, what was the data?
Would that be given the same FCS?
No, so this is we're using Hamming 7.4, but there was a new data word. So no longer are we assuming this. I want you to tell me what data word I sent if you received this.
Are we assuming only one error happened? Or at most one error?
If you're using Hamming 7.4, you have to assume that, yes.
Could I try to take a stab at it?
Yeah, go for it.
So so our received FCS would be 00011.
Yes.
But we would only detect an error if, I guess we would detect an error if there's a position that has a 1 where we would compare that position with our FCS, but there isn't a position that there isn't based on what we've created our FCS, there's no D equals to 1, a data bit where there's 1. So I'm assuming that you just think that the data is okay because you're not performing that. That's all I could think of.
I see. I think the curveball here is what should we call the frame check sequence generated by a data of all zeros?
000.
Yeah, I think that's a reasonable thing to say because you're basically taking the null XOR.
Oh, I see.
Yeah. Okay. So good. At the receiver, we generate the frame check sequence 000, but we read the frame check sequence 011. The XOR of this is position number 3, which means that the data that we guess was sent was 001 because this guy was an error.
Is that why we leave the data, like when you're counting from binary 1 to 0, that's why we leave 000 out, is so that for these cases, I guess?
That's a broad statement about binary arithmetic, and this is a very specific application of using binary.
Okay.
But I mean, it's why I call position 1, and not position 0, if you like. I
Okay.
call the rightmost position number 1.
Okay.
Yeah. Cool. There was an excellent video I think produced recently that I would like you to watch over the weekend, and it handles the n equals 16 case for Hamming codes. So I think I'll assign that as like a participation assignment this weekend. If you can watch the video that I'll link to you in on Canvas and just put your thoughts up on Piazza. It's another perspective on Hamming codes, and he does an example of n equals 16, which is really cumbersome for me to do on paper here. But I think that's an appropriate place to pause for today. We will talk about block codes and cyclic codes on Monday. I'll hang around here for questions, but I think that's the end of class. Yay, the power didn't go out.
That's good.
It's because you ended early.
Ah!
Yeah, give it a minute. Could you reiterate why it was 000 for that FCS received SCS position?
Sure. So let me switch over to something that I can write with a bit better. Okay. So we had 1, 2, 3, 4, 5, 6, and a whole bunch of zeros. Not that many zeros. 2, 3, 4, 5, 6, 7. Okay. The positions where the data was equal to 1, there were null. There were no positions that have that true. And I don't know if you want to take this as just the definition, but let's say that if I ever have to take the XOR of a number with nothing, that should be the number.
Okay.
And if I ever have to take the XOR of nothing with nothing, that should be 0.
Okay.
And yeah, so there is a bit of like, because I said so in here, but I also think that that's a reasonable standard to take.
But I see why. I guess I see why you would start at a position 1, because if you started at, let's say, if you had a 7 Hamming, you started at 0 to 6 or something. That's where you could. Is that why? I guess, or is that just that's just definition by binary? You would start.
Another thing is that like,
so that like
I want this to give me a number that's not in my position list.
Okay.
Yeah.
I think that, I mean, I'm perfectly fine with that answer.
Okay.
So, because it makes sense. It makes sense why, in order to create this case. So,
okay. Yeah.
And that fits, what.
It also gives us this nice result that if my data word is 4 zeros, then because I'm XORing nothing, then my code word is now 7 zeros. 1, 2, 3, 4, 5, 6, 7. And so we actually get the kind of like the picture we had on Wednesday, where 0 mapped to 000.
Okay.
Yeah, so this is also kind of nice. Like the 0th vector in the data word space maps to the 0th vector in the code word space. And it's also true for the all ones. So 1111, we XOR that, and we get all ones. So we also get this repetition.
Okay, that makes sense.
We also get a whole lot of others, right? We have 2 to the 4, so we have 16 possible data words. So we're going to have 16 possible code words, and they're all placed in the code word space, such that they each have a Hamming sphere of radius 1 that doesn't touch any other Hamming sphere of radius 1.
That makes sense. Okay, that makes sense. Okay, yeah. Thank you. I think that's it. I think I'm good. Have a nice weekend.
Thanks, Andrew.
So why this mapping works is just it just works out.
The explanation for why this works, I think, is really well covered in this video I'm going to assign you to watch. And the essence is what the check bits can be thought of are basically a binary search. And what the check bit in position, so this is position 1, 2, 3, 4, 5, 6, 7. What the check bit here is telling us is there an error in, say, this subsequence versus this subsequence? What the check bit here is telling us is there an error? I can't remember what it works out to with 7.4, but is there an error in other subsequence or that subsequence? And so what you get are these kind of like intermeshing binary answers. Yes, there was an error here. Yes, there was an error here, which means the error has to be in the intersection of those two areas. And that is all laid out way better in this video that I'm going to ask you to watch. But yeah, the key to the Hamming code detection correction scheme is where the check bits are placed.
Okay. Yeah,
Yeah.
I'll give it a look. Thanks.